Now let's resume 11.8 power series. In the first video clip, we talked about what is a power series and some lingos, and then what is the domain of the power series function or the intervals of convergence. And then we did some exercise problems to calculate intervals of convergence, and there the ratio test was used as the main tool. The interval of convergence is one of the three main topics that we have to discuss in this section. Let's move on to the other two. Second one is, well, this one, Theorem 2.1, calculus formula for power series. Basically what we can do is to take the derivative of each term to get the derivative of the power series, and the antiderivative of each term to get the antiderivative of the power series. Moreover, the radius of convergence doesn't change either way, whether you take the derivative or antiderivative. In other words, the interior and the exterior of the intervals of convergence will stay the same. At the endpoints, on the other hand, that's going to be a bit different story. In any case, you'll have to consider the endpoints separately. However, what usually turns out is if you take the derivative, then you end up losing the convergence of the endpoints, because as you can see, the coefficients end up getting increasing. And if you take the antiderivative, it's vice versa. As you can see, coefficient decrease. Consequently, you end up gaining some convergence at the endpoints. We're going to talk about this this losing and gaining the convergence at the very end in this kind of example, example 2.5, in these kind of examples. But that's something we're going to do way later, maybe video number 4 or something like that. The third topic is power series expansion, and we're going to spend quite a bit of time about deducing these formulae here in this clip. First, we begin with a geometric series formula. 1 minus x is equal to 1 plus x squared plus x cubed, and so on and so forth. And this is nothing more than a geometric series formula, because the common ratio is in this case x, and the first term is 1. So 1 minus 1 over x, 1 over 1 minus x, is nothing more than a geometric series formula. When is this series convergent? When the common ratio is less than 1 in absolute value, otherwise it diverges. Consequently, we get the interval of convergence, open interval, -1 to +1. How about the other formulae? Well, the second formula is relatively easy to see. All you have to do is replace x by -x, but the others all require a little bit of thinking, so let's consider them one at a time. Let's move on to the second formula here. And how do we prove that? From the first formula, which is a geometric series formula, this one, replace x by -x, because 1 over 1 plus x is nothing more than 1 over 1 minus of -x. So we end up with 1 plus -x, -x squared, -x cubed, and so on. We are replacing all the x's by -x's, and consequently we have this alternating sign, as you can see in the second line. Eventually we get the sigma expression. That was easy, and the others are not so trivial. Let's move on to formula number 3, which I think the most important, expansion of the logarithmic function. And that one begins from the second formula, as a matter of fact, here. And then we take the antiderivative, because log of 1 plus x is nothing more than antiderivative of 1 over 1 plus x. And 1 over 1 plus x is nothing more than, well, this series expansion, because of formula number 2, which we saw over here. And applying the antiderivative term by term, we have the third line. X minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4th power plus 1/5 x to the 5th power minus 1/6 x to the 6th power plus, and so on and so forth. And then we have alternating signs, so we end up with this sigma expression in the end. And what is the interval of convergence? Well, if you plug in x equals to -1, this is what you're going to get. You're going to get 1 plus 1/2 plus 1/3 plus 1/4 plus and so on and so forth. Because if you plug in x equal to -1, then let's see, all the negatives, excuse me, this is not entirely accurate. There. This is what you're going to get if you plug in x equals to -1, because this is -1, and then that will be +1 because you have negative. Sign V stay negative. And we have positive, but this is -1 to the 3rd power, so stay negative. So everything will be negative. Eventually we have something like this, and this is actually negative infinity. So what do we have? When x is equal to -1, we do not have convergence here. We have negative of a harmonic series. What if I plug in x equals to +1? This is what I'm going to get. 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 6 plus and so on. And this is going to be log of 1 plus 1. But what is log of 1 plus 1? It's log of 2. So we ended up with rather interesting identity. However, this is not really a good way to calculate log of 2, even though we have true identity here. The reason is because this summation is very inefficient way to calculate log of 2 because convergence is so slow. In any case, we have rather interesting identity that you should remember. As a matter of fact, you don't really have to memorize a separate formula. This one you have to remember and plug in x equal to 2, x equals 1, excuse me, and you're going to get log of 1 plus 1, which is log of 2, and then the right hand side we have the alternating series. Now, how about the third formula here? This one is very similar to the previous one, except the starting point is a little bit different. Instead of integrating 1 over 1 plus x, we need to integrate 1 over 1 plus x squared, because the derivative of arctangent function is 1 over 1 plus x squared, as you see over here. I mean, 1 minus x squared plus x to the 4th power minus x to the 6th power, x to the 10th power, plus and so on. This is the antiderivative formula for That's the antiderivative formula for 1 plus x squared. And that's, excuse me, what am I talking about? It's not antiderivative formula. It is power series expansion formula for 1 over 1 plus x squared. And that's obtained by replacing x by x squared in this formula number 2 there. The second version of the geometric series. So here, replace x by x squared, consequently replace all these x's by x squared, so we end up with powers, all the even powers, 2nd, 4th, 6th, 8th, 10th powers, and so on and so forth. So from there, if we take the antiderivative, then we're going to get, well, the third line over here. X minus 1/3 x cubed plus 1/5 x to the 5th power minus 1/7 x to the 7th power, and so on. We're going to get all the odd powers and odd denominators with alternating sign. And that ends up being the antiderivative, excuse me, that ends up being the expansion, power series expansion formula for arctangent function. Also, please remember this one. If you plug in x equals to 1 to each of these, then you're going to get 1 minus 1/3 times 1 to the 3rd power plus 1/5 to the 1 to the 5th power minus 1/7 plus 1/9 minus 1/11 plus ... And this is going to be equivalent to arctangent of 1. By the way, what is arctangent of 1? Anybody remembers? Arctangent of 1 is pi over 4. So if you want to calculate pi, well, this is not really an efficient way, but that's at least one way to handle that. 4 times this series will be equal to pi because of this identity. Although I must warn you, this is not really a good way to calculate pi precisely, because this convergence is very, very slow. So even though you take some thousands of terms, you're not going to get really accurate approximation of pi. In any case, there is a nice identity here that you should remember. Okay, we just went through a formula for arctangent. Now we have 2 more formulae to go, and these are both coming from derivatives. We begin with the original power series formula over here. 1 over 1 minus x is equal to 1 plus x squared plus x cubed, and so on and so forth, and take the derivative. And what is a derivative of 1 over 1 minus x? You can calculate it through the power rule and the chain rule. It'll turn out that the derivative is 1 over 1 minus x parenthesis squared. And that is equal to the derivative of the geometric series 1 plus x squared plus x cubed, and so on and so forth. So what do we get? Derivative of 1 is 0, derivative of x is 1, derivative of x squared is 2x, and so on so forth. We have this kind of series. Eventually we have that kind of sigma notation. That corresponds to this function, 1 over 1 minus x total quantity squared. If you have cubic power, for example, then basically you'll have to take the derivative once more, right? Which means you have to take another derivative of this. That could be something a little bit more complicated, but you can handle that. You can set up the derivative on the left-hand side and then go from there. The next one is pretty much the same. As a matter of fact, all you have to do is substitute x with negative x from the previous formula. Basically that's what it is, because this is parenthesis open 1 minus of negative x total quantity squared. So we end up with the sigma expression. In short, we have these power series expansion formulae, and among these I must say, let's see, geometric series formula is of course important, but rarely anybody makes any mistakes here. And otherwise, I must say this logarithmic function is the most important, but only to a certain degree. All these are important. In order to solidify all these understandings, let's do at least one problem here. How about this exercise? Okay, I think we have sufficient time to do one exercise, so let's go ahead and do that. How do we handle this problem? This problem is relatively similar to 1 over 1 plus something, which is formula number 2 in this power series expansion formula, the second one over here. Instead of x, you can substitute it by 9x squared. And that's basically what I did here. In this formula number 2, substitute x by 9x squared, and we end up with the following sigma notation and the final answer here. If you want to find out the interval of convergence, you can either use ratio test right over here to find out, which is not really recommendable, or you can just use this one. X has to be between -1 and 1 in this case, so what is substituting x? 9x squared will be between -1 and +1. 9x squared cannot be negative, so we have 9x squared is less than 1. So after taking the square root, we get 3x is between -1 and +1. Consequently, we get x is between -1/3 and +1/3. You can check the answer from the ratio test from the original, but that's kind of overkilling. We're going to do some more examples in the next video.